Ladies and gentlemen, dear respected colleagues, it's my pleasure having the opportunity of greeting you on the occasion of the celebration of another webinar of the series that in the Global Soil Partnership and the network INSAS, we are organizing, trying to develop contents that can be useful for our members and farmers and decision takers. This webinar is the fifth in a series of webinars, and it is aimed in general to raising the awareness of sustainable management of salt-affected soils for food security, agricultural sustainability, environmental protection, and climate change mitigation. This webinar, the webinar of today, is entitled Assessing Soil Salinity and Sodicity Using Remote and Proximal Sensing Data, has received a big attention from the members of the network, and a good number of registered participants is by now. And we recognize that the topic is of high interest of many of us, the practicing this mapping, or as well approaching this basic task to afford the soil salinity. The webinar itself is co-authored by Elia Scudeiro of the University of California, Riverside, in USA, Nan Lee of the University of California as well, Todd Skagg of the US Salinity Laboratory, Riverside, Sharon Benz as well from the California State University, in this case Fresno, by Aliasgar Montazar, University of California Cooperative Extension, and Dennis Corwin of the US Salinity Laboratory at Riverside. The presenter will be Elia Scudeiro from the University of California, Riverside, and allow me to shortly, introduce him, because he has a wide curriculum, and we will present him in a short way with the most important aspects of his curriculum. So Elia Scudeiro is an associated research agronomist at the Environmental Science Department of the University of California in Riverside, with a joint appointment at the USDA-ARS US Salinity Laboratory that is located also in Riverside. Before moving to Riverside, Dr. Scudeiro was awarded a PhD in crop science from the University of Padua, Italy, in 2013. Elia's digital agronomy lab used high-resolution geospatial sensing to study soil and crop processes across scales. This research includes using near-ground and satellite sensors to map soil salinity across spatial scales in irrigated farmland. Dr. Scudeiro's research advances sustainable site-specific agriculture management practices in water-scarce and salt-affected farmland in California and globally as well. The webinar is arranged in 2 sessions, as you can learn from the flyer. And this session will be devoted to the presentation of the basic knowledge. And the second session will be as well held by Elia Scudeiro, and will be devoted to hands-on training. And so I hope that you will enjoy and take profit of the content that Dr. Elia Scudeiro will show us. Thank you very much, Dr. Elia Scudeiro. The floor is yours.
Well, thanks very much for the introduction and the opportunity to be here today. I really appreciate the invitation to present on this topic, which is, as you mentioned, very relevant. And I hope that the information that I will provide today is useful for the attendance of this webinar. I greet you all from Riverside in Southern California. And just to give a little bit of a special perspective, as we are going to talk about maps today, we are located at the very south of the state of California, at the in the southwest of the United States of America. And the University of California, Riverside serves as an agricultural university, serves the agriculture in some of the key areas for agricultural production in the USA, such as the Imperial Valley, which is south of the state and borders with Mexico, the areas along the Colorado River, as well as the California Central Valley, which by itself is one of the most important areas for agricultural production in the States and globally. I also am, you don't see it because we have a lovely background from FAO, but I'm calling in today from the US Salinity Lab, which is the US Department of Agriculture Research Facility National Lab for basic research on chemistry, physics, and biology of salt-affected soil plant water systems. And the US Salinity Lab has been in the forefront for the past 50 years on the studying on understanding salt-affected system, water scarce systems, with research on water and salinity management, plant genetics and production, and as well soil and air quality. So today's topic is going to be revolving around general knowledge about soil salinity. We'll touch a little bit on sodicity, although it's not a major problem here in California. Proximal sensing techniques and methods to map and monitor salinity at the field scale, and then remote sensing technology to detect salinity on broader scales. Talk about some case studies for successful implementation of sensing technologies, and talk a little bit about the challenges and future directions in salinity and sodicity monitoring, leaving time at the end for questions and answers. Whereas the second module that we'll have next week will look into case studies on soil salinity mapping at the field scale and the regional scale, and we'll have some data analysis walkthroughs where I'll show the raw data and how to generate maps from raw sensor and soil data, excuse me. As previously mentioned, we have several contributors that played a role in preparing the webinar for today and next week. Dr. Jorge already mentioned them, but I would like to thank the co-authors of this talk for their contribution. And there's many others that contributed to the research that we are going to present today that are mentioned and acknowledged in the slides. So we'll talk a little bit at the beginning, as I mentioned, about soil salinity and sodicity. And just a caveat at the beginning here, I'm going to give a California perspective on this topic, right? Because we are here in Riverside in an area of California. We are the same latitude of Northern Africa for reference. We have in some areas of the state Mediterranean climate. Other areas of the state are arid and semi-arid. If there was no irrigation water, there would not be crops growing for most of the state. So the problems that we face here are like very particular for our state, but some of the lessons and technologies that we are going to talk about today might be applicable for a lot of other areas globally. So you may, have the chance to come and visit California, a lovely location for your tourist travel. And as you're crossing the state, we have a lot of open agricultural areas where just by driving, you may be able to see a lot of areas that are prone to salinity problems. And you could see like just driving around, seeing where like salinity accumulates in the surface, or you have soil crusting or or like how do you say the soil disaggregating as in this picture. But most of the cases here in California will be when you have fields where salinity can be seen in the surface, but also is not seen in the surface, but accumulates in the root zone. Because we are, as I mentioned earlier, working with irrigated agriculture, and water pushes salinity down, and salinity accumulates in the root zone. So it's not very apparent all the time that a soil is has a lot of salts in it, in the soil profile, but you will notice that the crop growth is stunted, is reduced in those areas. And another note, most of the tree crops that are grown in California, and we have like a very important production of citrus, of course, but almonds, pistachio, tree nuts. We grow a lot of tree crops here in California. Most of the tree crops are irrigated with micro irrigation, and that gives arisal to a problem of salinity that is much different from salinity from other irrigation systems. And we'll talk a little bit about it, but as you would walk like a micro-irrigated orchard, it would be very typical to observe these circular patches of salinity along the drip lines close to the water emitters. Salinity has been a problem that the US government has recognized as a limitation for agriculture for a very long time. Here I'm showing a map derived from a 1918 soil survey in the lower Imperial Valley. So as I mentioned earlier, this would be like the very south of California, on the area where my mouse is Mexico, and the north here is the Imperial Valley. And as you see from this survey, there was quite an effort that was taken by the University of California at that time and the US Department of Agriculture to make sure that salinity was assessed in the area to help growers manage the land sustainably, and to understand where agriculture could be most profitable in that area. So when we talk about soil salinity, we typically refer to the presence of major soluble ions in the soil solution. And here at the US Salinity Lab, we measure it as the electrical conductivity of the saturated soil extract, which basically goes as follows. We go out in the field, collect soils, we come back here in the lab, we dry the soils out and grind them and sieve them. And then we saturate them with the distilled water. And once the soils are saturated, we then extract the soil solution with a vacuum and analyze the electrical conductivity of that water extract. This allows us to classify soils in different salinity ranges, from non-salt affected to extremely salt affected. And this is important because it helps farmers and managers understand where their levels are at and how those levels would impact the growth of crops, because most of the agronomic crops grow well to okay, let's say, in up to moderate salt affected levels, whereas most of the soils that show extremely saline levels are not grown with commercial crops, with a few exceptions, of course. For example, pistachio grows fairly well even at the very high salinity levels. But in overall, the farmers are making an effort to keep their salinity levels at moderately saline or lower salinity levels. Globally, we have salinity being a problem for a lot of farmland. And what is more important is that 20% of the irrigated farmland is estimated to be affected by salinity. And that's important because the irrigated farmland is estimated to produce about half of the food and fiber that we produce globally. So on this 20% of irrigated farmland that is affected by soil salinity, 50% is found in 4 countries, China, India, Pakistan, and the United States. Here, just for a reference, I was talking about crop response to the salinity, and like the audience might be familiar with this graph here. It's some research that was developed by people back in the 50s and 60s, and the salinity lab scientists played a big role in this, in determining that when you have for most crop salinity, that's kind of like a limiting factor that limits the potential yield of a crop. And if you have crops that are sensitive to salinity, even at low level, you will start seeing a reduction in their production. But for crops that are more salt tolerant, they would still produce 100% up to certain salinity levels, and then they will start having lower yields as the salinity increases. And one exception is salt-tolerant crops that have sometimes lower productivity at very low salinities. They thrive at an optimal salinity level, and then as well they start having a decreased growth with the increase in salinity. So I'm calling from North America, and I would like to give some examples showing that, as I talked about, the US is one of the first countries that has like a lot of salinity problems in irrigated land, but this is a problem that we are facing across the entirety of North America. There's not a lot of reliable countrywide maps for Mexico, although some publications and some work is on the way for that. But there are several examples that show how salinity has been a major limiting factor for agriculture in Mexico, and I put some example papers over here. And then if we go all the way up north in Canada, in the Canadian prairies, salinity has been recognized as a big problem as like for quite a long time, and the Canadian government has been conducting efforts as well to map the salinity in their primary agricultural areas, which is the prairies. And in the US as well, I showed you, the US government has been recognizing this as a big problem for over a century now. And when I came to the salinity lab over 12 years ago, I noticed that in the hallway out there, right outside my office, as a matter of fact, we have this print that the US Salinity Lab made around the 1970 that shows all the salt-affected farmland, irrigated farmland in the western of the Mississippi River in the US. And as I'm pointing out here, California, you can see that over here in the Central Valley and some areas here in Southern California as well, we have quite some problems for salinity. And this map is color-coded for differentiating areas that are only salt-affected at the time and salt-affected, but also with sodicity problems. And what does that refer to? We can classify salt-affected soils and soils that have problems with salinity according to 3 primary indicators, such as the soil salinity, that is actually the electrical conductivity of the saturated paste extract, and the amount of sodium measured as the sodium absorption ratio, and the soil pH. So this table has classified soils according to this type of measurements. So if we have salinity below 4 decisiemens per meter, Typically, we are in non-salt affected soils as well if we have SAR below 13 and pH below 8.5. Salt affected soils are typically showing ECE above 4, but still SAR below 13 and pH below 8.5. Saline sodic soils, which we have some areas here in California that shows saline sodic soils, have a salinity above 4 and sodicity SAR values above 13. Then we have the case of sodic soils that have very high pH and high SAR, and then they are typically observed to have very low salinity. We don't have many of those here in California, but that's what we classify as a sodic soil. So a note here is that these type of measurements and are related to the chemistry of the soil, of course, and because a lot of irrigation water plays a big role in determining the status of a soil. We can, of course, assign soils to a certain class, but the issues of salinity changes over time. So there can be also changes of soil from non-salt affected soil to salt affected soil and vice versa. So to summarize again, salt affected soils have problems with soluble salts that are high enough to injure plants, reduce growth or reduce availability of water to plants, and sometimes direct specific ion toxicity issues. Whereas saline sodic soils are high multiple soluble salts and include specifically problems with the high levels of sodium. Here, it so happens that when you have this type of soils, irrigating with high electrical conductivity irrigation water will result in better soil structures. But then there's a more like a higher impact of salinity on the crop. As a matter of fact, we have one example later on in the presentation about one of these cases. And farmers historically have faced this problem by first dealing with the sodicity and then dealing with the high salinity levels. And then sodic soils, which we don't have too many here in California, have low to moderate total soluble salts, but high levels of sodium. So the effect of sodicity is mainly on the soil infiltration because sodium disperses the clays and breaks down the soil structure. So in these slides, we can see that flocculated soil, which is well aggregated, can take in a lot of irrigation and water infiltrates, whereas when you have a sodic soil, you tend to observe a lot of water ponding at the surface. And if you dig cores on those soils, you will have like a few centimeters of very wet soil and then dry soil below that because water doesn't infiltrate. And here in California, where you have sodicity problems in those localized areas with sodicity problems, waterlogging is a major issue. So in this slide, there's just an example in flood irrigated almond orchard that shows some areas with ponding. And you can note that there's a reduction on the tree performance on these areas, mainly because of the poor infiltration and then anoxia in the very top soil, and then unbalanced nutrient interactions between the plant and the soil. But typically, that's almost an extreme case. Other cases that you may be able to see by driving around here is some soil crusting or powdery soils where you have like isodicity, or not too much of a case here, but like some areas in Mexico, you have highly dispersed soil crusting, where you can see like that the pattern shown in the figure there in the picture. So This is a major problem, of course, because farmers have to face a cost of amendments such as gypsum to rebuild the soil structure, which can be a big cost to sustain agricultural production, and then as a to help the process, on top of gypsum, a lot of farmers are using cover crops that are deep rooted and salt tolerance that can help improve the soil structure. So there are several practices that are implemented in California to manage salt affected soils. First off, understanding the irrigation water, and then try to understand what type of leaching management needs to be done. And then picking up the right crop and variety for the soil and the farm that each farmer has, and what type of amendments that the farmer should apply. And then understanding then the type of irrigation management, irrigation delivery system, and so on. Obviously, each of these points comes with a lot of questions. Some of the example questions and considerations are in the slide, which leads us to the conclusion that we cannot really make these big management decisions without having knowledge of what the status of salinity is in these fields. So growers and farm advisors spend a lot of time in trying to understand and assess the levels of salinity. So salinity assessment is key for informed management decisions. But here in the US, how are we doing? What is missing? We have some salinity maps at the federal level that are produced by the US government. But those maps are dated and often based on a single core or pedon. And often those pedons that have chemical analysis are derived from non-irrigated lands. And this limitation basically is due to the fact that salinity in irrigated lands changes over time, and monitoring salinity with single cores at a resolution that is relevant for agriculture would be very prohibitive if the US government was doing it repeatedly and up to date. So accurate high-resolution information is needed for the root zone across scales, and the desired use include obviously agricultural management, crop selection, water management, but then also at the big scale, a large scale, the economics and social science analysis, and planning use change for converting land from one use to the other, or conserving land in ecosystems, and as well a big decision on water allocations between areas of the state, water districts, and so on. So with this in mind, the US Salinity Lab has had a lot of effort and resources put through finding ways to develop methodologies for expedite and accurate salinity mapping since the 70s. And we're now going to talk a little bit about the methods for near ground soil sensing for field to landscape scale mapping. And typically we carried out using sensors that can be embedded on field vehicles, such as a spray rig at the top, or like a all-terrain vehicle as shown at the bottom. So I showed this picture before. When you go look at it at the field scale, spatial variability of salinity is influenced by multiple factors, such as soil texture primarily, and then irrigation management, which is typically done at the field level here in California still. But these processes, especially texture, and in areas that are close to the bottom of the valley, so close to river systems, results often in high short-range variability of soil salinity at the field scale. And as I mentioned that earlier, most of the salinity accumulates away from the soil surface where it cannot be seen by the eye. So we need methodologies to measure the entire soil profile and being able to collecting and allow us to collect a lot of measurements in a field. So that then we can map having a lot of samples at our disposal. The technologies that we use here are either electrical resistivity methods or electrical magnetic induction method that allow us to measure the soil apparent electrical conductivity, which is a measure of the amount of current that can go through the soil when the soil acts as a conductor/resistor. And these type of sensors allow us to measure the electrical conductivity, apparent electrical conductivity of the soil at different depths of the soil profile, from very, very shallow topsoil measurements, 0 to 30 meters, to 0 to 150 centimeters, or even deeper. And this measure, as I mentioned, is a global measure of like the root zone and how the soil can conduct electricity. And typically the soil conducts electricity through three major pathways: the water pathways, the liquid pathways, the solid pathway, and the soil liquid interaction pathway. And any air in it kind of acts as a blockage for like electricity conduction. So this type of measurement is very complex because anything that can contribute to conductivity increases the sensor measurement. Anything that contributes to resistivity in the soil reduces this sensor measurement. So if you have higher clay content, you will have higher measurements. If you have higher water content, you would have higher measurements. With salinity, of course, you would have a higher conductivity measurements. But if you have gravel or sandy soils, or a lot of air pockets in the soil, then you would experience lower sensor measurement. But the good thing about ECA is that it's a fast measurement that you can take. It's very reliable. It's very easy to take and to mobilize, and then it's ideal, therefore, for soil mapping and monitoring in traditional application as well as precision agricultural applications. But because it's a complex measurement, calibration is needed to convert ECA to a target soil property, and in our case, of course, it would be ECE, the conductivity of the saturated soil extract. In regards to sodicity, whenever we go out in the field, we collect soil cores, of course, and we typically measure pH as well as the electrical conductivity whenever we have the extract from the saturated paste. But typically, we observe little field scale spatial variability of pH here in California. The vast majority of the soil have been here for many years, and I rarely observe soils that have pH higher than 8.5. And then if the surveyed field has a history of infiltration problems, or we observe like the federal database of soil that in the past fields have been classified with the higher SAR, then we would as well measure SAR in all the samples to also try to differentiate areas that have sodicity problem versus non-sodicity problems with each field. But in the case of pH measurements, and we don't do this here at the Salinity Lab, there are some sensors that are available in the market here in the US and globally for on-the-go pH measurements. And I put a paper here as a reference for the audience to refer to. But basically, this type of sensors can measure electrical conductivity with one sensor, and another sensor concurrently can measure soil pH. So those two combined information can help classify soils with sodicity problems, if any. So let's take a look on how the protocols that the Salinity Lab has developed for field scale salinity mapping and monitoring go. And this is a work that primarily Dennis Corwin has been leading for the past 40 plus years, but other colleagues such as Jim Rhodes, Scott Lesh, that have a lot of published work on the topics, and then myself, Todd Skaggs, have also contributed to in the recent years. These are the protocols for field scale apparent electrical conductivity mapping and ECA directed soil sampling that we have. One of the recent versions of these protocols are available in the methods of soil analysis by the Soil Science Society of America. Basically, it goes as follows. When we map salinity at a field, we would go out and collect hundreds, if not thousands, of sensor measurements across the field. And those are these black dots over here. And then we leverage the information about the spatial variability of these sensor data because we expect it to correlate with the spatial variability of salinity to understand where the relevant soil sampling locations are. And we have software, the ESAP software that is like a USDA Salinity Lab production that helps us identify very few representative locations, and in this case, 20 locations that can be used and then are sampled and then taken to the lab for laboratory analysis. And then using that laboratory data, we can pair it with the sensor data and develop linear models that allow us then to estimate salinity across the entire areas and over we measure with the sensor, and then we use geostatistical interpolation for mapping salinity at any location in the field. So once again, you start from the soil sensor measurements. Those are guiding the soil sampling scheme. Take the laboratory, the samples in the laboratory, do the laboratory analysis for salinity, and then use statistics to have a fit for the field between the sensor measurements and the laboratory measurements that allow you to map salinity across the entire field. So one example of like how these methodologies are used is for this field that that was an 80-acre saline sodic field in the Central Valley, and this has a shallow water table. And researchers Dennis Corwin and colleagues tested the use of Bermuda grass to reclaim these soils. From the 1990s to like the early 2010s. What they were using here is the drainage water with the varying salinity. So drainage water is collected from the other fields that have like better production and then used for irrigation in this saline sodic field. And then what they did is that they basically ran a survey for ECA and then selected the representative points and went ahead and used those representative points to map salinity and monitor salinity over time. And what they observed is that actually, as they were progressing with the irrigating with drainage water, the status of the soils in that field was improving quite a bit, as testified by these pictures, the first three pictures. But then we had a major historic drought from 2010 until 2016 here in California, and the soil jumped back to original status and higher salinity even more. And using this ECA directed soil sampling allowed the managers and the farmers and the scientists to notice how soil was improving and how quickly it went back to the previous status when this irrigation practice was terminated. And so it's just like a very good way to get quantitative data that is a representative of the phenomena that are happening in the field. One of the ways that you can then use this sensor data and these maps to make these changes evident to the stakeholders is to do change analysis over time. And in these cases, you can do it over the soil profile. These are just 3 crosscuts for the salinity maps between 2002 and 2011 at the same site, where you can see that in this like crosscut here in the front, from the surface to the bottom down to 1.2 meters, you have salinity that decreases at the in the very subsoil and increases in the subsoil, indicating that a lot of salinity moved upwards over there. So in conclusion, these sensors that are used at the field scale to measure apparent electrical conductivity are a good proxy for salinity. And once they are paired to soil cores, they can be calibrated to give very informative data and depictions of salinity as a snapshot, or even salinity changes over time. And why does this work? Typically, these sensors are built to measure these physical processes, right? These sensors are built to measure apparent electrical conductivity, and we know that when salinity is a problem, apparent electrical conductivity is one of the major drivers for the values that we measure with the sensors. And we would see that when we have a sensor map, like the theory behind it is that there is indeed a deterministic component in this relationship. So the salinity patterns, target soil information, put salinity here, are the ones that are determining the spatial patterns that you measure with the sensor. And as a matter of fact, the data shows, and we're not going to talk about it today, but in the questions, I can point towards some of the publications that we have on this. This type of relationship, like the slope of this relationship in particular, is stable over multiple fields. So even at the farm level, regional level, these are very stable. But there's a contribution at each field scale from a spatial random error that also contributes to the spatial pattern that you're measuring with the sensor. And what is this? This is basically determined by all the secondary factors influencing the sensor measurements, both from like the measurement side of things, as well as factors in the soils, and a random error that you cannot control. So this leads to the fact that although salinity is, excuse me, ECA is expected to be a proxy for salinity pretty much for an entire region, the calibrations that you develop for a single site are rarely expected to work on another site. And this means that, of course, anytime you survey a new site, you need to collect new data from this new site to calibrate the sensor once again. So we'll move now to talk about the broader scale remote applications with remote sensing. And when you move to broader spatial scales, obviously you have to deal with the short scale variability that you observe at the field scale. But then you also start staggering different contributions on this overall spatial variability, such as management. And here I have an example, and excuse me if I rotated it just for graphical purposes, display purposes, but like this is the north here goes right to left on my screen. You have 2 sites over here on the same soil series that are owned by 2 different growers that are belonging to 2 different irrigation districts. And this is just like, this road in between the 2 sites here is just the difference between the 2 irrigation districts. This example in particular is on pistachio, and the two pistachios orchards are pretty much the same age. And you can see from this aerial figure that the southern one, the B, the one on the right, has low soil salinity, whereas the one to the left, just because of the different management, has a worse performance and higher salinity in this case. So management plays a big role from a field to field. So kind of like a block type of way. Each field is managed separately, and each field should kind of be considered separately when you're trying to assess salinity because of these management differences. But then, even broader scales, pedogenesis, geomorphologies, the climate, evapotranspiration, weather, and so on, also play a very big role. An example here is the Central Valley, right? Riverside is south of this map. San Francisco, just for reference here. The Western San Joaquin Valley and the San Joaquin Valley are the southern portion of the Central Valley. Salinity is rarely observed in the eastern side, but mostly observed in the western side because all the soils come from the alluvium of this coastal range that were anciently bottom of the sea soils that have been then contributing to the alluvium of the western side of the San Joaquin Valley. And then another note here is on the use of remote sensing for different applications, right? If you read the literature, most of the applications are on soil crust or topsoil. And that is a problem that, I mean, as the very rich literature shows, has some challenges, but is fairly resolved. I mean, there's always improvement to be made, of course. But you can use classifiers on images to identify white pixels. Here we have an example from one of our publications to identify soil crusts. Or you can use the regression methods to also identify soil crusts. But typically, one of the problems with this is that this is a very dynamic type of phenomenon where some mitigation or rain could contribute to making soil crust disappear and come back later in the year and so on. So this is just an example with the PlanetScope for the south of California, 3-meter resolution, August 2023 and January 2021. In one image, you don't see the soil crust. In the other image, you see the soil crust. But as I mentioned earlier, we don't focus here at the Salinity Lab on topsoil salinity assessment all too much. We are more interested in mapping or developing methods to map root zone soil salinity because that is more relevant for agricultural soil management. And from our experience, it's very hard, maybe even like I don't know if it's possible to determine the whole profile soil salinity from surface information. Because from all the data that we have, and this is just an example from like that early 20th century soil survey that I showed you earlier, we have measurements of the topsoil and measurements for the whole soil profile. And typically this, there's not like a great correlation statistically that to tie one to the other. And here you have the example where you have the topsoil salinity in the y-axis, and the x-axis you have the whole profile down to 1.8 meters. And you can see that there's some like, correlation patterns, but this is not sufficient typically to allow you to estimate the bottom, like the whole soil profile from the topsoil. So this is not like an extreme problem because obviously you cannot just go and dig soil cores everywhere to map salinity in every single field in an agricultural region. One of the things that helps us out, at least here in California, in other areas in the globe, as a matter of fact, because this is a publication from from Australia, the one on the right, is that the root zone soil salinity, unless there are major management changes, tends to be fairly stable over the years. So there are some vertical movements throughout the season, some minor movements of salts leaving the soil profile, but typically you would see over multiple years, in the short span of years, salinity, average root zone salinity levels remaining fairly constant. And with this in mind, that's one of the basis premises on how we use remote sensing here at the Salinity Lab to create regional scale soil maps. Because we start with the assumption that we can use remote sensing time series over a short number of years to map the average levels of salinity over the soil profile through the performance of the plant. And how do we do it? This is a proof of concept study that we developed under a grant from the US Navy that was interested in understanding the extent of salinity in the Central Valley to possibly convert those land to production of biofuel. So we surveyed 22 fields in 2013 in the western side of the San Joaquin Valley. And this amounts to almost 6,000 Landsat 7 pixels with the soil salinity information that we then use to make a remote sensing model. As you can see, all those fields are located across the valley. And how did we do the salinity measurements there? As I explained before, this is an example from another site where we have hundreds of measurements of the sensor that allow us to select representative locations where these one circles here were to do soil sampling. Then we do sensor to salinity linear modeling to estimate the salinity map. And then we use kriging or other interpolation methods to estimate salinity at the same resolution and on the same grid as the satellite product that we are using. And a note on this, this is fairly important, especially if you're working with the resolutions in the tens of meters or like hundreds of meters. Because we have several examples that show this, and Mario Guevara, that is now professor in University UNAM in Mexico, that used to be a postdoc here with us at the Salinity Lab. He showed this on some data from Southern California, but we have other publications that show it for the Central Valley. Whenever you take point measurements of salinity and you compare them to this average salinities at the resolution of a satellite that you're using, there's often a mismatch between that. So like the single point is not representative of the average of the pixel that you're selecting. Therefore, it is very important to first map salinity across an entire field in order to have a more reliable measurement of the average soil salinity that corresponds one for one with the pixels of the remote sensing product that you're using. Mainly here, in the past, we've been using surface reflectance of crops as an indicator used for the salinity models. And then that allows us to calculate several vegetation indices using, from the visible to the near infrared reflectance, with understanding that you can recognize a healthy crop versus a stressed crop using these measurements. But also with the understanding that this is a relative crop status measurement, that obviously stress versus non-stress, but also different phenological stages, or if the soil is more visible or not, and even the soil type, the crop type, the variety, they all play a role in determining the surface reflectance that you see from the satellite. As a matter of fact, great example, this paper from Wageningen that shows that, obviously you can use thermal as well to map salinity, but a takeaway from here that I'm not sure if it's in that paper is that still thermal is also affected by other plant processes such as water stress and others. So obviously, you need to also calibrate that type of measurement for relating it to soil salinity. In the recent past, we've also used other sources such as like the Sentinel-1 microwave radiation data. But overall, any of these data, they really are not a direct indicator of soil salinity or any other process really. So you always need a ground truth and a model that tries to extract the information from the satellite data to the target information that you want. So particularly, we've used vegetation indices, and I also always recommend to test several because different ones may be working better for different areas in the planet. As a matter of fact, very commonly used NDVI or EVI are shown to perform fairly okay globally. There are like so many other vegetation indices. We developed the CRSI here at the Salinity Lab because it's shown to perform very well for our type of climate and ag systems. Several have been tested this CRSI in their studies as well in similar areas globally, and it's been performing well for them as well. But what I recommend is to test many and then try to land on the one that works better for the region that is under study. So going back to the idea of salinity as a limiting factor, we kind of like use the Liebig law of the minimum as a guiding principle for understanding how crops perform over time over a field or like even like at the single location at the pixel level, with understanding that a crop is bred to produce, but the potential yield is reduced by lack of nutrients or is brought down by the presence of stress in the soil or in other environmental stressors. So looking at this and looking back at that salinity tolerance graph that I showed earlier, you can see has like, in this case of salt tolerance crops, there's no reduction of potential yield from salinity until like a certain threshold. And then salinity starts reducing potential yield because the crop starts experiencing stress. But this line does not mean that you go out and you measure the salinity in the soil and you will get this much yield reduction guaranteed. Actually, no, because this is just the line of the maximum yield that you can observe for that salinity level. Of course, you can observe much lower yields because of other compounding effects or environmental stressors, lack of nutrients, or whatever can happen at the specific growing season for that field. And this was first described, to my knowledge, by a great paper coming out of Wageningen again in Spain. I think, as a matter of fact, I didn't put the map here, Dr. Jorge, but I think it's in the area close to Valencia where they did this for rice, and they monitored the yield across several fields in the region. And what they observed is that with increasing salinity, you would see that the maximum yield for its salinity class was always decreasing. So they said, okay, yeah, boundary line analysis is a good way to describe what the potential yield can be given the different salinity levels. But as you see here, even at low salinity, they did observe low yield, and probably because something else went wrong for that specific field in the specific year when they observed this data. So with the understanding that we can then use like vegetated land NDVI time series or CRSI time series vegetation indices to give us an idea of the crop performance over a site, we took 7 years of data. and we took a look at it, and this is like amounted to 42,000 pixels over the study area. And obviously, you can see some variability, like from higher performance to lower performance, right? But again, if you bin it for increasing salinity levels, you will start seeing that phenomenon that we just talked about. That increasing salinity will be acting as a ceiling to crop performance. And overall, you can see this graph that is very similar to the Maas-Hoffman salinity tolerance. But actually, if you zoom in and you interpret it with the eye of an agronomist, you will understand that there are several of these curves along the profile. And why is that? Because the growers are not ignorant to the overall values of salinity in their farmland. So they try to do crop selection to address the salinity level, the overall salinity levels on their farmland. So you will see different tolerance curves in this overall data set. So how do we take this information and translate it at the pixel level? So the pixel level will have over multiple years several values of your remote sensing vegetation index from low to high. And our idea that we tested was, what if we take the highest value, which is going to tell us what is the potential yield over multiple years for that pixel. And with the understanding, as we talked earlier, that under similar management, the salinity stress over the root zone would remain fairly constant over a short amount of years and act like as a permanent reduction to that yield potential. And then also that we can measure the plant performance, this time use CRSI, but also NDVI, EVI, whatever works best for the region. So this vegetation index then is going to be maximum when all other influencing factor, transient stressors, are going to be at the minimum. So here, in this case, in this very pixel, this one location, in this example, it so happens that year 3 has the maximum CRSI. And if we keep that permanent stress constant, that would, conclude, let us to conclude that there was like a very little transient stress on that area. So we can use this as an indicator for the salinity, the average salinity in the root zone. So we tested this idea using this multi-year maxima approach versus like an arbitrarily picked best performance or using single images, single years, average of the entire year, whatever. And this always outperforms the correlation between salinity and remote sensing for a variety of vegetation indexes. So like this approach is fairly universal, like it doesn't depend on the vegetation index. But how can you further improve this? Because this is like a big cloud where you observe this like a downward relationship between the vegetation index and the salinity. How do we improve that? But we have available covariates, such as like the crop type or management type, the weather, meteorology, the soil information and management, as I said. And then the best model that worked out as for like data-driven model for our area was a model that explained EC as a function of the maximum multi-year CRSI, and then the weather in that year, as well as if available, like the soil texture. And that allows us also, and also the crop type and management that we had. So this allows us to map salinity with a fairly high R-square and low prediction errors over the entire region, which then you could like be very excited about like these good results and go and say, okay, let me just apply this model everywhere in my region. But before we do that, it's the responsibility, of the map makers to make sure that these models are robust and that are validated thoroughly. So we'll look at it in the hands-on session next week on how to do some spatial cross-validation of these type of methods independent soil sampling as a validation. And also something that we've done, but not that we're not talking about, going to talk about, make sure that you test what the geographical extent of your extrapolation power is. So testing this model on different geographical areas. And then and only then you can go ahead and publish the map as a tool for decision makers and farmers. And we publish the map in a different publication, and it's an open access publication, as a matter of fact, that can be found on the California Agriculture, a peer-reviewed journal for University of California. But one of the good things that that is the responsible thing to do is to go and ask the growers, because as I mentioned, most of the growers, at least here in California, have a general idea of what the salinity is in some of their areas. They don't have the funds to cover salinity surveys in every single field, but they do have spot measurements every year to map salinity in some of the fields. So we went to this grower that has this farm and has average measurements from like, gridded sampling from these sites. And you can see how there's a good match between the soil measurements from the farmer on the right and the model from remote sensing on the left. So only when you are confident on the robustness of the model, you can then publish the map that shows what the salinity problems are for the Western San Joaquin Valley, as a matter of fact, as shown here. And again, this is explained fairly in detail in this California Agricultural publication that is open access. I have a note here that says no orchards included. And I was mentioning earlier why we should make sure to extrapolate these to different cropping systems. We noted that the performance was fairly low when applied to orchard systems, so we did not include that in the map. And we thought that was the responsible thing to do in that case. So why was it responsible? Because once you publish a map and you put it out in the wild, it has a life on its own, of course, and people use it to do very important measurements, such as investigating the economic and policy implications of salinity over a region, such as example in this peer review paper, or for larger decision making about water allocations and water accounting for projecting land use changes, such as in California, we are facing water scarcity and we are talking about retiring some of the soil. So having information on soil salinity can help decide which soils can be retired or used for different purposes. Or it can help managers to track changes of land quality and degradation over different years. So it says this example here in the Broadview Water District. They used to be the most the highest producing, highest yielding water district in California and in the US for many years. You can see like a maps here, like still black and white figures, but here colored area photography from 2006. What happened though is that they were small enough that they decided to sell their water rights to a neighboring water district, and they retired the entire land between 2006 and 2007 and 8. And you could see that the soil quality then degraded quite a bit, even visibly. And even in 2011, you can tell that there's that land is not doing well, primarily because of the shallow water table in the area. But there's a salinity lab survey for the entire district in 1991 compared to the 2013 map that we made. You can see salinity changes. What is important there, just as a note, that all the non-salt affected areas, slightly salt affected areas in 1991 have become moderately to strongly salt affected soil. So as a take-home message here from the management standpoint, you have soils that have been irrigated for decades and they are productive. and in just a matter of like a few years of mismanagement or different type of management can return to very highly degraded and unproductive levels. So some limitations very quickly. And we can talk about it a little bit more in the questions or next week as well. Orchards. We just saw that, you know, orchards have a different land cover. We service some orchards, and we noticed that the values that we were measuring were much lower than what predicted with remote sensing. And then we did a lot of work on improving the ground truthing of this orchard system in micro-irrigated systems with some publication in the early 2020s. But we simply haven't found a good way to map salinity in orchard systems as well, because they are like so different from agronomic and other horticultural crops. Secondly, if you have non-salt affected soils that have high spatial variability and they suffer from you know, excessive leaching, so water nutrient deficit and or water stress, you will see a spatial variability in the map that doesn't really correspond the spatial variability of the ground truth. Although the values here are not diverging on an average at the field level too much. And then lastly, those pesky halophytes, you could say. Other people, this is a great paper from China, observed that, you know, because of like lower performance of halophytes, a lower salinity level, it's very hard to determine if a low performance is due to high salinity or low salinity. There's kind of like a dual interpretation there on the data. So if you're including halophytes, pasture land in the models, you should be aware of that. Whereas for cropped, like traditional crops, this is not observed. Secondly, what we did there was a 30-meter resolution, but we are working nowadays with 3-meter resolution, 10-meter from Planet, 10-meter resolution from Sentinel. We use other satellite data in the past with high resolution. High resolution doesn't mean always like a better representation of the soil processes. So there's always a need to determine what is the best spatial resolution for a site. In this paper, we described how we kind of determined that the best match between the spatial patterns captured by satellite and spatial pattern captured by ground truthing were observed around 20 to 30 meters for fields in the Central Valley in California, but it might be different with different spatial structures in different areas of the world, of course. And then spatial resolution has also an impact on the footprint of your analysis. MODIS has been used in the past as a very good tool because it has daily data that can be used. But in many of the cases, even with very large fields here in the US, typically 1 pixel covers multiple fields. And if you have drastic differences in management, you will notice that you have like mixed pixels that are not very informative if you have two cores of pixels. So to conclude, these remote sensing methods allow you to, looking at the limitation again, sorry, we have uncertainty of prediction at low salinity values. Halophyte reflectance of properties are problematic. We don't focus on tree crops on the published work. The selection of satellite product is very important and might be lead to different results according to the geographical area that you're working with. The understanding of root zone is different for different crops. So we just use like a 0 to 1.2 meters in this study, but it should change perhaps with different cropping systems. And this multi-temporal data analysis is not a universal approach for soil salinity, but it's a universal approach for permanent stressors. So a lot of researchers doing heavy metal research, especially in China, have picked up on this method, as a matter of fact, and they use it for heavy metal mapping. So with this in mind, with these limitations, also we can really conclude that these methods are fairly reliable for mapping salinity on agronomic relevant ranges. Although we need indeed further research to improve accuracy. And machine learning, when you have big enough data sets, is a very promising tool. AI is a very handy tool at the moment to help these type of endeavors. Obviously, as an agencies, universities, countries start having data over multiple years using spatial temporal models and the availability of data that tracks back to the 70s from satellite data can help develop spatial temporal models to help track salinity changes over time. These methods, as I said, have been developed for California and the US Southwest, but they have been tested and adopted and improved thanks to the community in other areas globally. So with this, thanks so much for your time. And I think we have some time for questions, and I'm very happy to take any questions from the audience. Thank you very much.
Thank you very much, Dr. Scudeiro, for your interesting presentation. And now we have time for several questions that have been formulated. Maria, could you present the questions and Dr. Scudeiro give the answers, please?
Yeah, so Elia kindly agreed to stay here a bit longer so that he can address most of the questions. So let me start with, there were many questions in the Q&A box. So let's try to address at least most of them. So first of the questions was how the environmental factors like soil moisture and temperature can affect remote and proximal sensor readings. So I think that you partly addressed this question, but the temperature was not maybe mentioned.
The temperature for the apparent electrical conductivity?
For both for proximal and remote sensing.
Yeah, no, sorry,
moisture and temperature. What is the influence for the readings?
The sound dropped for a second. I apologize.
Okay.
Obviously, there are physical laws that correlate that relate the measurements of apparent electrical conductivity in a soil to the soil properties, moisture, salinity, so that the solutes in the soil solution, the soil type, and as well temperature. They play a big role on how the output sensor measurement will be. Typically speaking, I mentioned that we have these protocols of recommendation from the salinity lab. In those protocols, there's a clear detail that temperature should be kind of accounted for. And typically we do that by covering the sensors and try to insulate them from sun temperature and carrying out all soil surveys way in the middle of the day when the soil temperature kind of like is stabilized. However, there is always going to be a little bit of temperature changes in the soil and in the sensor as you're carrying out your on-the-go measurements. But those type of influences can be then accounted for in the statistical modeling as spatial trends or as part of the spatial random error that you should account for. And that, for that particular reason, that is one of the influencing factors that make it so that you cannot really use one calibration from one field to a next field over.
Okay, thank you. So the next question is, how much will be the price of using the sensor per hectare?
Oh, that's a question that changes very much on the market. Let's say that since people started developing these sensors, the price of these sensors have become very affordable. And I'm not going to mention any trade because I don't want to give any endorsement because of my position, of course. But there are several manufacturers that nowadays have sensors that are below $5,000. And those sensors can be used. And obviously, the cost per hectares depends very much on who is making the survey. Some of the big growers here in California have their own sensors that they're using for surveying. But there are some companies, soil scientists, certified soil scientists, that have the sensors and they use it to map, and then they price the surveys to the growers per hectare. But once again, the problem on these, the limiting factor is the amount of ground truth that is needed to map these soils and to calibrate these soil sensors. Because one of the things that I was actually discussing with one of my colleagues, Sharon Bennis, that contributed to this talk, is that these sensors, from our experience, are fairly robust, and if treated well, they can last for many, many years. We had units that lasted for over 20 years that were just retired because of connectivity problems with newer GPS units. But because you can keep them for so long, the price then becomes like minimal if you get to use them for very long. It's a very steep barrier at the beginning, but then the real cost becomes the labor force and the cost associated to laboratory analysis.
May I add something? That the patent protection time for some of the most popular devices has exhausted, and so people can do that legally, build up those instruments.
Okay, so the next question is related to the time of the sampling. So, what is the appropriate sampling time after irrigation, as soon as water can be stay in the field for quite a long time especially in sodic soils, in the morning? And it's the first question. And then about the pH, so it's in one block. Is pH important for mapping? So does it influence the readings, pH?
To my experience, pH doesn't influence the readings too much. You could observe some statistical correlations due to other factors that are related to the physical properties that are influencing the readings. But in terms of timing, water content is very crucial. So we have a lot of data that shows that as the soil gets drier, the correlation between the sensor and the soil properties that you want to map are degrading. Dennis Corwin and the colleagues, and I ascribe to that as well whenever I do my field work, recommend that these surveys are done when the soil is fairly moist. So around 50% of the field capacity. Going with a drier soil is a little bit harder. And obviously, this can be problematic in areas that have like a very low infiltration rates versus areas on the field that have much higher infiltration rates. So like there's kind of like some practical trade-offs that the soil scientist has to consider on a case-to-case basis. But like ideally, you want to be on soils that are close to field capacity, so that you can get the most information out of those sensor measurements.
Okay, so clear. Then next question is about, there were two questions, but I think that they can be addressed simultaneously, about the depths. When you use like proximal or remote when you use remote sensing. So how can Landsat data, optical data, penetrate to the soil if there is a land cover or existing crops?
Even if there's no crops, yeah.
Yes, even yes, indeed. And also, what's the depth of soil of the soil? To which depths we can consider the soil, let's say, salinity prediction when we use satellite imagery. So in salt-affected soils, for which depths we can more or less be sure the result of predictions.
So, well, very well put. The satellite is a surface reflectance property, right? So it's either the soil surface or the crop. But as I detailed, we are trying to infer the salinity for the entire root zone through the performance of the crop. So the satellite just see the surface, but the crop growing on the soil is experiencing the salinity levels over the entire root zone. And obviously, you can be more sophisticated and given like the crop that you're working with, try to model different contribution at different depths according to like, root zone distribution models. But typically speaking, you could say that like, the first meter, 1.2 meters, depending on the crop, sometimes even shallower, what you're seeing through the crop refers to the depth of the root zone. So the crop will respond to the salinity levels that are present in the root zone. So the only way to use remote sensing to get deeper measurements directly or like indirectly, but in a mechanistic manner, is to go to analyze, interpret the response of the plant to the soil over time.
Okay, thank you. So, and the next, there is also a block of questions which are related to scale and spatial resolution. So I will ask them all, and then we can go one by one. So first, when estimate, so when there was a research, they made a research estimating soil salinity from satellite data. So they used Landsat 8, Sentinel-2. So the spatial resolution was a key factor that affected the accuracy of soil salinity assessment. First, let's say if you agree with this conclusion.
We have it. I went over it a little bit too fast towards the end, but that's what we saw as well. We did like a multi-resolution analysis, and yeah, I second that. But it's not a universal thing. It's very region specific. So you go from resolution to 2 meters and resolution of 100 meters. And our matrices here indicate that the best resolution for this field and fields that have like a similar geomorphology, 20 to 30 meter was the ideal resolution for that site. But it could be that in fields that have a different spatial structure, higher resolution is better, or fields that have very long range spatial variability, you can get away with like a coarser resolution, right?
Okay, so the question was also about the not high, but quite large resolution for salinity. So 30 to 30 meters, it is quite a large pixel for salinity variation. So why you considered this spatial resolution in your studies? And then continuing this question. So would you suggest integrate remote sensing and near sensing techniques for mapping electrical conductivity, ECE? So extract. Then
but we can stop here, Maria.
Yes,
two
there is
different questions.
Yeah.
So the question on the resolution and the 30 meters, primarily when we did this, Landsat was the primary product that we considered. All the analysis that we did using higher resolution satellite sensor indicated that 30 meter was a good resolution. And again, we are still trying to provide measurements at the field for field scale management or management zones that are way larger than 30 meters. Obviously, having high resolution helps disaggregate, shapes of the field like a little bit better and try to like it helps you segmentate the environment much better than as I showed earlier with the 250 meter MODIS pixel that covers multiple fields with just one shot. But really it's true that it's better to have higher resolution, but then you have to butt heads with the computing limitations and the actual resolution that is then used by the users of the product that you want to do. So, you know, you can always upscale your data, but really, like, if you're trying to make depend on the scope that the model has. And then apologies, you had a second question that I already forgot.
Yeah, so actually it wasn't one, let's say, one question from one participant, but yes, they were a bit different. So so having this, it was some sort of suggestion that if you have 30-meter resolution remote sensing, so maybe it can be seconded by the near sensing mapping. So you should use both of them,
But
like a proximal and remote at once, so that to improve the prediction.
I mean, everything can be done, but the question is always that you have to keep in mind is, why are we doing this? Are we doing this for the sake of publishing a paper, or are we doing this to map salinity? And so if you have access to a near ground sensor and your interest is to map field scale spatial variability, I would suggest that the satellite data can be skipped altogether, because generally speaking, the on-the-go sensor from near ground sensing maps salinity very well. If you have cases where that is not the case, then you can do some data fusion. We do that for scientific publications, but for like real life applications of farm advisors and soil scientists, if your interest is on the field scale, then I would suggest going with the near ground methods. If the interest is from an agency level to develop broad scale soil mappings, then the combination of near ground for calibration and remote sensing for mapping over the entire region is the way that we recommend.
Yeah, so next question, I think that you already addressed it in your challenges, let's say, of the using this remote and proximal sensing data. But still, maybe you can elaborate more, that the methodology and the challenges are not the same when you map orchards or annual crops. So can you maybe
what is not the
elaborate? The methodology, so we cannot develop the methodology which is developed for annual crops. It cannot be used for orchards. So, and vice versa. So maybe you can elaborate more on this phenomenon.
Agreed. Yes, that's very true. So we spent some effort. Excuse me from scrolling fast. I'm going to stop at the slide when we have it. There we go. I show this very, very fast. Most of the tree crops here are under micro-irrigated systems. And these show a very localized, high, short-scale spatial variability of salinity. And typically, as you get far away from the drip lines, you would have like low salinity by the drip line and increasing salinity as you get away from it. And Bert and Isabel from the California State University, back in 2005, they did some very good characterizations, among the first ones doing those, with a lot of transects showing the soil profiles. And they basically, like, a rule of thumb is that salinity accumulates laterally to the drip lines and then deeply down the soil profile. And then you can have like the irrigation leaching from the drip, but as well, if you also have winter flood leaching, when you have water availability during the winter time, you also have a lower salinity in the alleyways. We developed methods and to use solid transport modeling. That was the work of Theodore Bogici for his postdoc, to determine where the salinity is most likely to be according to the different irrigation methodologies and the soil types and salinity water, as well as Dennis Corwin has updated protocols for salinity mapping in micro-irrigated orchards. So it's a very long conversation, and I think Dennis is scheduled to give one of these webinars in the future. So I'm pretty sure that he will cover the newer protocols for micro-irrigated orchards, but basically they are very different from sprinkler irrigation and flood irrigation and other types of irrigations on agronomic crops.
So there is no solution. I mean that there is no approach that we can transfer the knowledge that we received from one crop to another. So it is just, so always
well,
we should...
the principles are very similar, but the type of ground truth that needs to be done is very different. Yeah.
Okay. So then there were questions regarding not non-optical like other remote sensing data. So can radar signal from Sentinel-1 be useful for salinity mapping? And also the hyperspectral products, how useful are they for studying and mapping salinity?
Yeah, so the Sentinel-1 products, yes, but with the same, I would recommend with the same caveat that a single image is not truly informative for like a regional scale assessment. Might be for a field scale assessment, but not at the regional scale. So these time series type of analysis are what we would recommend with thermal and Sentinel-1 data as well. Yeah, so just like keep on going with time series analysis would be like my recommendation to go. And Maria, sorry for the second half of the question.
Hyperspectral.
Oh,
so
yes,
radar and hyperspectral.
Yeah, the hyperspectral data is very interesting to me. I've had like a little bit of experience, and typically you can get very good results from hyperspectral data. But what I observed is that when you want to make models that go beyond like very niche systems, when you have different factors contributing to the signal, you need to have the same precautions that you would use with multispectral. You might have better results with hyperspectral just because you can narrow down the bands for your local regions of interest, but the processes are not too different from my experience here in California.
Then the questions that are appearing just recently. So can you mount the sensor on the drone?
Well, the payload for most drones is like not big enough for this type of sensors, I would say. But there are there's people that do aerial measurements with similar technologies like time domain electromagnetic sensors that have like deeper ranges of penetration than like the sensors that we use. But there's nothing that precludes that, but just the payload for most of the sensors and most of the commercial drones at the moment that are like, inexpensive enough for wide adoption. That's the bottleneck there.
Yeah, so then the question regarding the modeling that the difference between Kriging and machine learning models like SVM, support vector machine, I suppose. So I don't think that you should give the lecture about this method, but do you consider one of them more appropriate or less appropriate? Do you have any experience in using different predictive models?
Well, so we use Kriging at the field level, and as a rule of thumb, we rarely use any machine learning data, any machine learning method when we have field level data, because I think it's not, I mean, it's an overkill in general, and Kriging does very well for field specific applications. We use machine learning when we have larger data sets. And with the scope of perhaps reducing the number of samples that might be needed to calibrate surveys at new sites, or to better calibrate interactions that just like the simple linear models, as I showed in the proof of concept example, don't capture as well as machine learning would. But I recommend using machine learning only when you have very large data sets that are encompassing very large, like a wide range of interactions and environments and copy system and such. Because otherwise, those models don't extrapolate well in unmeasured locations. If you know, when if extrapolated over environments that are not very well represented in the ground truth samples.
Okay, thank you. So we are done with the questions which are related directly to the assessing salinity using remote and proximal sensing, but there are also some questions more, let's say, general. So if you have some more minutes, we can also address them if you can. So the question is regarding the threshold values. So can we consider the threshold, the ECE between 2 and 4 decisiemens as non-saline for vegetable crops, whose salinity threshold is less than 2 decisiemens? Yeah. And these crops lose substantially, the yield is decreasing in this range between 2 and 4. So what is your...
I second that. Yes, I just typically non-salt affected soils are classified for land use management for like at ECE equal to 4, but indeed several crops are sensitive and have a lower salinity thresholds. And as a matter of fact, we do a lot of vegetable crop production here in Southern California. And let me see if we have the map here. Along the Colorado River, here in this area between California and Arizona, the Imperial Valley, those are the salad bowls of America. We produce most of the winter production of vegetables here. And salinity assessment here is done because salinity, we irrigate with the Colorado River water that has some salt contents in them. And we want to make sure that we leach salts sufficiently before planting vegetables, because otherwise the production will be stunted quite a bit. But at that low salinity levels, you have sometimes also problems with like specific ion toxicity with the crops, such as like avocados, for example, that are very sensitive. So that for like a number is you know, like a rule of thumb for land management classification that has been developed in the past, but obviously us as agronomists know better, so we need to help growers manage their land according to the cropping system that are present locally, of course.
Yeah, so the last question that I will ask here is regarding the equipment. Is there, so the equipment that we can use for the proximal soil sensing, is there anything of this that is available internationally in international markets? So,
yeah. I use units that are from Europe and Canada. As a matter of fact, we don't use. I'm not using currently any American-made sensor in my suite. So yeah, they are available globally. Just need to find a manufacturer that fits the budget and the application that you have in mind.
Okay, so actually there were some other questions which were raised in the last minutes, but I think that we can address them later. Yeah, that's all from my side.
Dear Elia, well, if I can make a resume of your speech, it is needed to have in mind what will be the use of the activity that you will perform. And it is quite different if you are making a regional map of the, how to say, the resources you have and their limitations, and if you are advising farmers for production. And this is because, well, the intensivity of data to be collected, it differs a lot. And as well, as you mentioned, this area close to me, yes, that's true. It is the Delta River Delta River of Ebro, and this paper of Casanova. Now I'm acting as advisor there, and they have such. Well, the problem seems to be more complex that can be solved by remote sensing.
Oh, yeah.
And they are using now these drones with the multispectral camera on the airborne. And as well, they are using such small devices to measure in the crop the normalized vegetation index. But it is true that it is a mismatch in the scales that you measure things. And from Sentinel, they get such information that is affected by atmosphere absorption and dispersion. And with the sensors, they get other that is more affected by geometric issues. And with the handheld spectrometers, they get others. So, and they have difficulties to make all this info matching. And but it seems that is a promising activity for very detailed scale for solutions for farmers, because they're related to the precision farming. No, what do you think?
Yeah. But yeah, so this is gives me the opportunity to conclude with a general recommendation to this. So we talk about the use of these sensors, these big data sources to help us map salinity, help the farmers manage their soils. But my warm advice to the audience is that these are tools in the belt of an agronomist to help interpret the physical processes that are happening. So go into it with a good understanding of what the processes are and are expected to be, and use this tool as an aid to interpret those and scale up different spatial extents. Because otherwise, if you just go heads in and you just let this data drive you, you might be blinded by some secondary and unwanted influencing factors that are determining the output of these sensor measurements. So first off, let's get very comfortable with the expected agronomic processes in your area, and then use these tools to enhance that knowledge to help give better information over wider extents.
So thank you very much. And before closing the webinar, can you make a forecast of what will be the content or activity in your next session?
Yeah,
Please.
sure. We saw a few examples on field scale mapping, as well as the remote sensing for the entire region. What we're going to take a look at is data collected with near ground sensors over multiple fields, and see how we can calibrate the sensor. So I will show you my GIS, and then most of the stuff that we'll do is on Microsoft Excel, just to show some correlations and such. Look at how calibrations from one site may or may not be used for other sites, or once we calibrate regional models with remote sensing, how do we interpret the data, how we validate the data, and so on. But basically, I will be showing from my end, my screen, my data, how I walk through the data, explaining the data sources and such to show numbers rather than just the concepts that we talked about today.
Thank you very much. Well, with this information, we have arrived the time for the completion of the webinar. And I want to thank especially to Dr. Elia Escudeiro, to Dr. Maria Koniuskova for the task of arranging for the questions, and to all participants that attended and as well made very interesting questions. And we will meet next week. So thank you very much, and all the best for all of you. Have a nice day.
Thank you and goodbye. See you next week.
See you next week.